Hello everyone, I am Rohit. I'm doing Ph.D. in the Department of Solid State and Structural Chemistry unit in IISC, and I'll be the TA for the present course Bonds and Bands in Solids, where I'll be taking up assignments, weekly assignments preferably. And today I'll be solving the assignment number 1 for the present course. I'm sharing the assignment with you people. So these questions are multiple choice questions, and we have to select one question, one solution out of this given options. So the first question says that which of the following is not valid in the context of Born-Oppenheimer approximation. So first of all, one has to understand what Born-Oppenheimer approximation says. First thing is that the nuclear motion is extremely slow as compared to the motion of electrons. And this is why, courtesy of the fact that mass of nuclei with respect to the mass of electrons is very greater than 1. So nuclei in a solid move much slower than electrons. So option 1 is correct. The second option says that excited electronic states do not have the same equilibrium nuclear distance as compared to the ground state. Now to understand this, we can understand in terms of a configurational coordinate diagram. Let's say I'm drawing energy as vertical axis and configurational coordinate, that is the vibrational coordinate of the atoms in molecule. Now if one plots the ground state energy, let's say this one, and let's say is the first state, and the further excited states, and this state has a minima at this position. The second state would have a minima longer than that. So this second option is also correct, that excited state would have larger energy and therefore would vibrate much more vigorously and with a greater amplitude. Third says that the electrons see an almost stationary nuclei. Yes, that is true, because of again the same reason, that mass of nuclei with respect to the mass of electrons is extremely large. Now the fourth option here says Born-Oppenheimer approximation works best when the ground and excited electronic states are nearly degenerate. Now let us consider this scenario in the following manner. Again, let's say vertical is the E, and we are plotting the x-axis as the configurational coordinate. And if the first state or the ground state of the system is composed of this way, having minima at 2 vibrational amplitudes, and the first excited state goes in such a way, this let me say as the ground state, and this goes as first excited state, and let us put a condition that the 0 point energy for this system is above the barrier. This is the barrier between the ground state and the first excited state, and the 0 point energy is above it. Now when the nuclei vibrate, the nuclei present at this position changes the electronic surface from first excited state to the ground state, and when coming back to the original position comes from ground state to the first excited state. Now this is not allowed by Born-Oppenheimer approximation, because what it essentially says is when nuclei are moving, the potential experienced by the nuclear motion, but the potential due to the nuclear motion is extremely it changes extremely slowly, because of nuclear motions are very slow, and therefore electrons do not feel any excitations or any changes in their energies, and therefore this particular scenario breaks down the Born-Oppenheimer approximation, and therefore the correct option for the first question, that is in fact the not valid option, would be option number 4th. Now if let's move on to the second question, which says that which are the terms in electronic Hamiltonian, one should note the word electronic here, that are missing from the total Hamiltonian. Now let me write the total Hamiltonian for a many body electronic system, which consists of kinetic energy of the electrons plus the kinetic energy of nuclei plus the repulsive potential energy between nuclei and nuclei plus the attractive potential energy between nuclei and electrons, again plus the repulsive energy between electrons and electrons. Now in the Born-Oppenheimer approximation we found that nuclei moves very slowly as compared to electrons. Therefore, velocity of nuclei is extremely slow as compared to velocity of electrons. Now, velocity is very intimately related to kinetic energy of the particles, and therefore the kinetic energy of the nuclei is extremely small as compared to kinetic energy of the electrons, and therefore this term, that is the kinetic energy of nuclei, is extremely small and can be neglected from the Hamiltonian. The other term that I am considering here is the term of the potential energy, repulsive potential energy between different nuclei. Here what we can see, that if velocity of nuclei is very slow, let's say than the electrons, then nuclei, we can say that nuclei do not change their positions, right? And if nuclei do not change their positions, the repulsive potential energy they feel amongst themselves is constant. For V, in fact, capital V, the potential energy between nuclei and nuclei is a constant. And if we consider this term as a constant, and we know that Hd above is the Hamiltonian, and which is an operator, so if a constant term, that is Vnn, let me write the Hamiltonian again with in this way, and if we add this Vnn term here, Vnn, which is a constant. Now if a constant term is added to an operator, it doesn't changes the eigen functions of the operator and just adds on a constant value to the eigenvalues. So this Vnn can be eliminated from Hd. So the final Hamiltonian becomes V and electron-electron repulsion. This Hamiltonian is the electronic Hamiltonian, and if you note that we have eliminated the kinetic energy of nuclei and the potential energy of nuclear-nuclear repulsion. These two terms have been eliminated from the total Hamiltonian that is here. So if we go back, right, so the correct option would be, are missing from the total Hamiltonian, those terms are the electron-electron repulsion term, in fact the kinetic energy of the nuclei and nuclear-nuclear repulsion. So option 3 would be correct, right? Let's go to question number 3. Now self-consistent field method is another name for Now as we know that we have found the electronic Hamiltonian to be composed of kinetic energy for electrons, potential energy in nuclear electron repulsion, plus potential energy of electron-electron repulsion. Now this Hamiltonian is still complicated to solve due to this electron-electron repulsion term. So what Hartree-Fock approximation does, it says that electron-electron repulsion is weak, first thing, and second is that electrons are moving independently. Now what these two approximations have an impact, let's take an extending the page and let's see. Now electrons also have a probability distribution. Let's say probability distribution of the kind, let me just write it this way, phi 1, phi 2, phi 3, where these phi's are orbitals. Okay, now we can write the wave function for the system to be a product of these single electron orbitals, right? We also assume that electrons are moving in a potential of all the nuclei and an average potential of other electrons. Fine. Now what this has an impact, if I calculate the V average potential at position R1 due to, let's say, another electron at position R2, it would be probability of finding the electron at position R2 multiplied by the potential energy, R1 minus R2. Okay, and this goes for all the position R2 can take. Summation goes over all the position. Now this P of this PR2 probability that we have seen is nothing but phi star R2, phi star R2. Fine. Since this R2 is a continuous variable, summation changes to integral. Okay, so this sum here is transformed into integral phi star R2 phi R2 e square R1 minus R2 d cube R2. Fine. Now if we extend this analogy, average potential due to the other n minus 1 electrons into the system becomes V average due to rest of n minus 1 electrons becomes, and this V average to the rest of electron is acting on electron number 1 that we are considering. So I can write V average acting on electron 1 is sum of all the other electrons. So the dummy index would run from all the other electrons leaving first electron in and the probability would be of finding all these electrons at their respective positions multiplied by the potential energy, R1 minus Ri to dq by I. Right. So the non-interacting problem, because we have assumed that electrons are free to move, so this non-interacting non-interacting problem becomes kinetic energy of the electrons, mass of electron, del 1 square, that is the first electron, minus the attractive term z alpha e square, or R1 minus R alpha plus V average, this one, at R1. This is our Hamiltonian, right? This Hamiltonian acts on phi R1 to give our eigenvalue equation as phi R1. Okay. Now, since we know that these phi star R, phi R gives probability density or charge density, right? So how do one solves this equation is, first is we guess some charge density, and we put into this Hamiltonian over here and obtain a set of equations, obtain a set of these equations for each electron into the system. Okay, obtain equations for each electron. Fine. And after solving those n equations, we get set of phi I, and obtaining a set of phi I, and we know that phi I correlates with the charge density of the system, we calculate the charge density and we feed this charge density again into the system. Now, before feeding this charge density into the system, if the initial guess of this charge density is say very close to the charge density evaluated at the end, then we say that we have a self-consistency loop, and if not, we feed this charge density into the system again and starts a loop. So this method of Hartree-Fock approximation is called self-consistency loop in this regard of solution of the equations. So if we go again to the top of the question, this self-consistent field method is actually another name for Hartree-Fock approximation. So correct answer is Hartree-Fock approximation. Let's get on with the fourth question, which says that which of the following approximation leads to separation of electronic and nuclear motion. As we have already know, as we have also discussed, Born-Oppenheimer approximation does that. Question number 5 says that which of the following is not a correct assumption of Hartree-Fock approximation. As now Hartree-Fock approximation also accounts for the fermionic nature of electrons, and therefore one has to include the antisymmetry of the wave function, that is wave function wave function of particles, say R1 and R2, would be minus, or if you interchange their positions of R1, right? So it is not symmetric for fermions. Then also the electronic wave function can be a single Slater determinant. That is also a valid assumption for Hartree-Fock. Each electron moves in a potential due to all the fixed nuclei and an average due to all other electrons, as we have also discussed. The Hartree-Fock approximation assumes that electronic wave functions are symmetric, which is a false assumption, which is in the case of Hartree-Fock. So the correct option is answer question number 4, and also the spin is ignored in this Hartree-Fock approximation. Moving on to question number 6, what is the electronic configuration of the ground state of anion of hydrogen molecule? Now if one does MO diagram for hydrogen molecule, one would find that if I draw a MO diagram for hydrogen molecule, that is 1s atomic orbital of hydrogen 1 and of hydrogen 2, they each contribute 1 electron, and we have this bonding situation here. This bonding MO is called sigma 1s orbital, and the bonding anti-bonding MO is called sigma star 1s orbital. And since 2 electrons are already filled in this, so we write 1s2. And so the configuration for hydrogen molecule, neutral hydrogen molecule, would be sigma 1s2, sigma star 1s0. But if we add an electron into the system and make this as a hydrogen anion, then H2 minus would become sigma 1s2, would remain sigma 1s2 in fact, and the additional electron would go into the sigma star 1s, sigma star 1s, and 1 electron has gone with antibonding, so we say in this way. So the correct option would be option number A. Next question is, which of the following statements about 1s bonding and antibonding MO in hydrogen molecule is correct? Now as we have seen that in above, that we have a bonding situation for sigma 1s2 and antibonding sigma 1s in fact, and antibonding for sigma star 1s. If one writes the sigma 1s molecular orbital as a linear combination of atomic orbital of 1s plus 5 1s of H2, this is a constructive overlap of the wave function, and sigma star 1s would be 1s of hydrogen 1 plus 1s of hydrogen 2, and I should correct it, there is a destructive overlap, that's why it's antibonding. Destructive. So if one goes to draw electron density diagram for this thing, one would find that if this, well, let me choose a different color in fact. So if we have this as hydrogen atom 1, and here we have hydrogen atom 2, then the orbital wave function for 1 go like this, okay, and other go like this. Net if I draw like this, we have a finite density of electrons in between the two nuclei. But for a destructive overlap, wave function is positive and the second hydrogen wave function is negative, and the net result of this would be charge density is high, 0 in between, and high in the other end of the molecule. So at this point we have 0 charge density, and this 0 charge density means a node in the system, a nodal plane in fact. So the correct option would be anti-bonding molecular orbital has one nodal plane, while bonding orbital has 0 nodal plane, because there is no node in the system. Question number 8 discusses says that the energy of atomic orbitals in an atom. Now, as we have seen above here as an example, that when there was a node in the system, that is in case of 5 star 1s, when there was a node in the system, we drew the MO diagram. The energy here of sigma 1s is less than energy of sigma star 1s. So if there are nodes into the system, then energy of those atomic orbital increases, and this atomic orbitals, analogy also goes with molecular orbitals as well as with atomic orbitals. So energy of atomic orbitals increases with increasing number of nodes. One can also take this example as 1s, 2s, 3s. So if you increase the number of nodes in the system, 2s has one node, one nodal plane. This is 1. 2s would have this thing. 3s would have 2 nodes, this area and this area. So if you increase the number of nodes in the system, the energy of those atomic orbitals also increases. So, this is a very simple fact. Then we have, according to Huckel theory, next question is question number 9. According to Huckel theory, for a 4 hydrogen ring, the energy for a 4 hydrogen ring, we have 4 atoms here, the energy of the lowest state and its associated wave function for a negative T is given by. So lowest state of a system, lowest state is actually the ground state, and ground state is most constructively overlapped state of wave functions. And if we do the same analogy as we did for a 4 hydrogen atom ring, then what do we have? The most constructive state which we find here is 5-1s, constructively overlapping with 5-1s of hydrogen 2, constructively overlapping with third and for fourth. And also in the previous example, we found that when we drew the diagram for hydrogen 1 and hydrogen 2, 1s here also, these 2 electrons, when come to combine these molecule in the bonding molecular orbital, there is a stabilization energy T. This we call it T, and since it is an energy of stabilization, the sign is negative. And there also goes a destabilization energy for the anti-bonding orbital. In this case will be similar to T. Therefore energy of sigma star minus energy of sigma would become T minus of T would be 2T. So the difference between the anti-bonding and bonding is 2T. And same analogy can be extended to a 4 hydrogen ring also, and therefore the the energy of the lowest state and its associated function would be 2t, and the wave function would be this. Okay. The next question, question number 10th, deals with Bloch theorem for one-dimensional ring. And we know that Bloch theorem, as we have read in the course, is given by psi k at nth side, the wave function at the nth side is equal to ikna multiplied by the function at the x position. Another equivalent representation is also available in literature. Now, another equivalent representation for this, as is very easy to understand, is the fact that the wave function at x position is governed by a periodic function, periodic lattice function, because solids are made up of atoms arranged in a regular manner. So this function is a periodic function of the lattice, and we have a plane wave. Fine. And this k here is actually a vector in reciprocal space. So correct option here would be option number 2nd. Psi kx is a periodic function ux. Ux is equal to u at position x is equal to u at position nth position x plus na, and k is a vector in the reciprocal space. So correct option would be option number 2nd for the Bloch theorem. Now, for a ring of n atoms, question number 11 says, for a ring of n atoms, how many discrete values of k are there? Now, let's say for a ring of n atoms, first atom present at this position, second, third, fourth, fifth, and so on, so on, so on, so on. Final atom is, let's say, at nth position. So what Bloch theorem says is the wave function at some position, say n, is given by e to the power I k n a psi kx. Now, due to this periodicity of this ring of n atoms, we achieve the same state. So after capital N atoms, the wave function x plus capital Na would be equal to the wave function that we initially started, because we have come around at the same point. Therefore, if you compare these two equations, e to the power I and Na would there is a factor missing here, I k na. Now from this equation, what we know, at nth position, after n atoms, we have the following equation, but the wave function at nth position and wave function at the first position would be same because of the periodicity, and therefore I k na becomes 1. And when such equation becomes 1, we know that the argument, that is k and a, has to be multiple of 2 pi, where r is an integer. So therefore allowed value of k would be 2 pi r divided by na. And if one puts values of r here, you will find for r is an integer, if r is 0, k becomes 0, and when r is 1, k is 2 pi by na, and since r is an integer, r can be minus 1, so we have plus minus 2 pi by a. On the similar note, we also have plus minus 4 pi by na, then plus minus 6 pi by na, and so on. Fine. Now this goes on There's another thing which we have to note here, is that now we know that kna is equal to 2 pi an integral multiple of r, but how long we can go on like this way? So r would be kna divided by 2 pi. So r would be restricted by the highest value of k, and we know that the k values are restricted in the region of 0 to pi by a. Okay, there is a closed bracket on the 0 side and an open bracket on the pi by a side, because if there are closed bracket on both sides, then they will be related by a reciprocal vector, which will connect these two, but it's not possible. So k is restricted by pi by a. Okay, k is pi by maximum value which we can have is in fact let me no, let it be. Then in a by 2 pi we have r is restricted by n by 2 less than or equal to n by 2. I think it varies between 0 and pi by a. Let me correct myself. So when n is even, let's have two cases, and when n is odd. Now when n is even, the k values we had 0 plus minus 2 pi by na plus minus 4 pi by na, and so on and so forth. The final value which we have here would be now if I write 2 pi by na then 4 pi by na, let me rewrite the term 4 pi by na in the manner that 2 multiplied by plus or minus 2 multiplied by 2 pi by na plus or minus 3 multiplied by 2 pi by na, and so on and so on. Last term would be, now as we know that r is restricted by n by 2, so last term would be n by 2 multiplied by 2 pi by na, and since the last term is a single term, I think this goes here. Initially I was correct. So yeah, it goes as with this one. Yes. So the last term is only one term. Okay, and the previous term is again 2 into n minus 2 by 2. There is a plus here, and we have 2 pi by na. Okay. So now what we have one state corresponding to k equal to 0. We have two states corresponding to this, again two states corresponding to this, and so on and so forth. Finally we have a one single state corresponding to the last, and we have two state for the last second term. How many times these two appears? Now there is a 1, there is a 2, there is a 3, so on and so on, and there is a term n minus 2 by 2. So these 2 appear n minus 2 by 2 times. Then we have 1 and 1. So total becomes equal to n values, n number of values. So k can take n number of values when n is even. But now when n is odd, k goes as 2 pi by na plus or minus 2 into 2 pi by na, and so on. and since k is restricted by n by 2, and when n is odd, n cannot take an value n plus 1, so n has to be n minus 1. Last term would be n minus 1 by 2 pi by na. Now this time we will be having a plus or minus sign because we are not dealing with the last term. So we have a single state for 0, 2 states for 2 pi by na, 2 states for 2 into 2 pi by na, and so on, and finally 2 states for the term nk is equal to n minus 1 by 2 term. These are again very easy to find out, n minus 1 by 2 terms, and since every term has 2 states, we have the 2 and finally 1 for the k is equal to 0. So we have again n values of k, and so we have n values for k is equal to when n is even, and n values of k for n when is odd, right? And we have again seen that k values are separated by the multiple of 2 pi by na. So the correct option for a ring of n atoms, right? How many discrete values of k are there? There are 2 and 2 and 2 and n. There are n discrete values, n separated by 2 pi by na. So correct option would be option number 4th, n discrete values. Just erase it. N discrete values spaced by 2 pi by na. Next question we have is, for an infinite one-dimensional chain of atoms, the energy dispersion relation is given as. Now for an infinite chain of atoms, infinitely one-dimensional chain of atoms, we can write the tight binding wave function for the system as summation of n atoms e to the power I k n a phi 1s x minus n a. Okay. Now assuming that these single electron wave functions phi's are orthonormal, that is phi 1s x minus n a phi 1s star x minus n a dx, in a single dimension we are talking, so we have dx is equal to delta n a, ortho normality condition. So our function psi k of x would become, now this orthonormality condition would translate into the prefactor to the wave function as 1 by root over n into e to power the I k n a phi 1s x minus n a. So this wave function now has been normalized by the prefactor 1 by root over n. Now how energy is found by the variational principle. Psi k h psi k divided by psi k in the bracket. Now this term, the expectation value, we can find as follows. Now psi k multiplied by psi k would 1 by root n, and 1 by root n would give me n outside. The two summations, let me call the dummy indexes L and M. Phi, and the remaining inside would be phi h phi x minus na, and the exponent associated with the two wave functions would pile up at the end. I k minus L plus ma. Okay, this term inside here is nothing but HLM, okay, which would become minus of t for m value as L or plus or minus 1, and would become 0 for otherwise. Okay, and if you plug in these values to our above equation, we find that if we put m as l plus 1, l plus or minus 1, we are only remaining with terms ika plus e to the power minus ika into t. Okay, so this ika exponential minus ika, if we multiply and divide by 2 here, this term is nothing but a cosine term. We have cos ka, in fact 2 cos ka into t, summation goes at l. Now this summation goes from l1 to n, right? Now n times this summation goes as 1 1 1 and n times it is calculated, so it gives a prefactor n outside and the remaining inside term is independent of the summation, and n cancels. We have 2t cos 2a as the energy dispersion, and since we have orthonormal wave functions, psi k become 1. Therefore ek is 2t cos ka, and therefore this energy dispersion relation will become et as 2t cos ka, and our answer will be 3. So in this present class we have solved the I think 12 questions for the assignment number 1, and this would be the end of this present class, and we would meet in our second class where I'll solve the assignment corresponding to module number 2. So till then, bye everyone.